alpha minus u infinity sine alpha minus 2 theta, and the imaginary you get the cosine from here, right? So plus gamma cosine theta over 2 pi a equals 0. Two equations for the stagnation. One thing that we immediately get from here is that gamma, remember gamma is unknown. I added gamma deliberately. So gamma controls theta stagnation. Any theta in this equation is theta stagnation. Add the stagnation point. Add the stagnation point, okay? So the amount of gamma you add controls the theta stagnation. That's fine. Let's continue over there. Get the velocity in the z plane. So I have the velocity here in the zeta plane. Let's get the velocity over there in the z plane. So your w pi in the z is your this thing divided by f prime. F prime is easy. Here is your f. If you go here, here is your f. Differentiate this with respect to zeta, you get 1 minus a squared over zeta squared. Okay? So this is divided by 1 minus a squared over zeta squared. So let's do this. I'll multiply up and down by zeta. So I have u infinity e negative I alpha zeta minus u infinity e I alpha a squared over zeta minus gamma over 2 pi I over zeta minus a squared over zeta. And if you notice here the real part, look at the real part. Let's do it. The real part is u infinity cosine alpha times zeta. The second term is u infinity also cosine alpha. It's a squared over zeta. The imaginary part, here is I, u infinity sine alpha zeta and what else? Plus a squared over zeta, correct? Minus gamma over 2 pi. This is all divided by the same denominator. And you can see here immediately that these two guys go away for the first term. So I have u infinity cosine alpha minus, here is the imaginary part. So the real part is taken care of now. The imaginary part has two terms up. And you can realize here zeta plus a squared over zeta. This is what? This is what? Zeta plus a squared over zeta. Come on. Yeah, this is f, this is z, right? This is z. Because what am I trying to do here? This is already the complex potential in the plate domain, but it's still in terms of zeta. Zeta is, I don't want to see anything in the cylinder domain. I want to see everything in my realistic domain, in the plate domain. So what I want to do is just replace zeta in terms of z, okay? In a clever way, just to save some steps. So already here they go away, luckily. Here naturally they replace. So this is actually my z, the coordinate in the plate domain. I still have this part down there. So this is minus gamma over 2 pi divided by zeta minus a squared over zeta. So this is the only remaining thing, is that to replace this term in terms of the z. Okay? In terms of z. This is easy. I mean, just some manipulation. I'll call this term d, whatever. So you have zeta plus a squared over zeta. This is my transformation z. Zeta minus a squared over zeta. This is what I just interested in, what I call d. And these two guys I will add and subtract. So z plus d is what? Is 2 zeta, right? Z minus d is what? Is 2a squared over zeta, correct? So if you multiply both things now, z squared minus d squared is 4a squared, which means that d, which you are interested in, is a square root z squared minus 4a squared, and we have plus or minus depending on the upper surface or lower surface. So I got rid of d. So actually, here is my velocity, complex velocity, is u infinity cosine alpha minus I u infinity sine alpha z, it's gamma over 2 pi divided by square root. So this is plus or minus, be like this, z squared minus 4a squared. We got stagnation point, we got the velocity everywhere, okay? So if you have the velocity everywhere, you can get the delta Cp, and from the delta Cp you get the lift. We already know that it's rho gamma, or the Cl is 2 gamma over 2 u infinity c. Any questions so far? Any question, please? Any question? I'll wait for you for a few seconds to just ponder upon it, and if you have a question, please come up with it. So we did what we want. We got the velocity field. This is the velocity at any point in the z domain. Give me your coordinate in the plate domain, I immediately give you the velocity components, u and v. In particular, on the plate, z is equal to sum x for varying x, and y is equal to 0. You get the velocity distribution on the plate. From the velocity distribution on the plate, you can get the pressure, integrate the pressure to get the lift, but we know the answer a priori. It's simply rho u gamma. Okay? Any question, please? Any question so far? So what's the issue now? Right? Gamma is unknown. This is the main issue.
Professor Tom,
Yes, Tyler?
how did we come up with our initial z equation?
Oh, this is very good. So this is a whole area of research. Is you have a complex shape. How can I map this complex shape to a circular cylinder? Why circular cylinder? Because the flow around circular cylinder is very well known. And if you can do this mapping, you're done. This is already a research area. Luckily, this has been discovered a long time ago. This is Joukowski transformation. He came up with this that maps the circular cylinder to the flat plate.
Can you prove it?
Yeah, please. I'm sorry.
I mean, can you prove it?
You prove what?
Prove that the flat plate can actually be mapped into a cylinder. Is that
Here it is. It's very simple.
Just as this?
Yeah. So this is 2a. This is negative 2a. I put on the cylinder zeta equals a e to the I theta, right? Do you agree with this statement? This first statement? Just substitute it here. A e to the I theta here, and a e to the I theta there. A squared divided by a gives you a. Okay? So you have e to the I theta plus e to the negative I theta. The imaginary part cancel and you get real only. It means what? It means that all the points on the cylinder for theta from 0 to 2 pi maps to what? This thing. Give me any theta on the cylinder, I give you just a real number. So all the points on the upper surface map to all the points on the upper surface, and vice versa. So the thickness is 0. So a cylinder of radius a through this transformation will map to as just a straight line of length 4a. Okay? This is easy to prove. What is hard to get is that this guy, a priori, what is the transformation? You know, given a shape in the right hand side, given a shape over there, what is the transformation that maps the cylinder to that shape? Like I said, this is already an area of research. And it doesn't have, it cannot be any function. It has to be a conformal mapping, right? It cannot be any function. It has to be differentiable and one-to-one. Because otherwise, it doesn't work. It doesn't make sense. Okay, so we reach this point. And if you think about this point, it has to be stressed enough. Few lessons here. So first, this is potential flow theory, right? Potential flow alone cannot determine you the amount of lift, period, right? Why? Because my lift simply depends on my circulation. Here is your lift coefficient. And I want to know this guy. The flow, the theory itself doesn't provide any means of determining gamma. In fact, it didn't even feel the existence of gamma, and I had to add it. I had to add it deliberately, intentionally, right? I had to impose it. The theory did not identify the existence of a circulation from the beginning. When I solved the flow field here around a circular cylinder, irrespective of the angle of attack, if you put here U infinity, what will happen? I mean, the cylinder is symmetric. It doesn't matter, right? So even if you put the flow at an angle of attack, the potential flow theory itself does not feel the generation of a circulation. Period. It cannot alone give you how much lift is generated. This is very important point.